Hi there. I'd like to talk to you now about electric fields, and this is a basic introduction to that topic and a review for Physics 2020. So, charged objects, as we covered in our Coulomb's law lecture, charged objects don't have to be touching each other in order to exert forces on one another. In fact, they can be a distance r away. Theoretically, the force has an infinite range, although practically the force goes as 1 upon r squared, and so it goes off to 0 as the charges get infinitely far apart. Now, we can think of non-contact forces as field forces. The concept of the electric field was actually first thought of by Michael Faraday, who was trying to explain how things that aren't touching could still exert forces on one another. So what we say is that a source charge establishes an electric field in a region of space around the charge. What the field looks like, how the lines point, depends upon the shape of the source charge and how far away or close you are to it. Then, if you have another charged object that we consider to be an infinitesimal test charge, and it enters this region, then the electric force is going to act on that test charge, and it's going to push it in the direction of the field as long as it's a positive test charge. Now, generally what happens is we consider the test charge as a field detector. Now, in order for that to be true, and for the test charge to come in and not change the configuration of the electric field, then the test charge would have to be infinitesimally small in magnitude compared to the source charge that established the field. In practice, this doesn't actually work. I mean, you have a fundamental limit on the size of an electric charge, 1.602 times 10 to the minus 19 coulombs. And so, it's not too practical. You can think of it as a theoretical construct, though, when you draw your electric field lines. Now, the electric field is defined as the electric force on the test charge Q per unit charge. And we would write this as an equation, a vector equation. F, the force, is equal to Q times E, the electric field. Remember, Q is the symbol that we often use for charges. So, E is the field produced by the source charge or the charge distribution, which is separate from the test charge. It's important to remember that the presence of the test charge isn't necessary for the field to exist. It's a field detector, but it's not necessary. The field has already been established by the source charge. Similarly, we could use that test charge to figure out what the electric field is like in a region without really knowing about what the source charge is like. So if you can measure the electric field, then you can map it out, and you don't even really have to know what the source charge looks like if you can't figure it out, for example. You can use the test charge as an electric field detector. So, the direction of the electric field is defined as the force on a positive test charge. Now, if you had a negative charge, it would move anti-parallel to the direction of the electric field. Positive charges move downstream on electric field lines, and negative charges move upstream on electric field lines. Since we have an equation, F is equal to QE, if you do some simple dimensional analysis, you can find that the units of the electric field are newtons per coulomb. Now later on we'll talk about voltages and electric potentials, and when we do that, you'll realize that the electric field units could also be written as volts per meter, but we're going to talk more about that later. Now remember, Coulomb's law defines the force between source and test charges, or any two charges really, as F is equal to K Q1 Q2 over R squared in the R hat direction. Reminding you what those variables stand for, K is the Coulomb constant, 8.99 times 10 to the 9th Newton meters squared per Coulomb squared. Q1 and Q2 are the magnitude of those two charges, and R is the center-to-center distance between the charges. R hat is a unit vector indicating that the force is along the line connecting the two charges center-to-center radially. So if you use the equation F equals to QE and you combine it with the equation for Coulomb's law, then what you would end up with is the test charge canceling out. And what that would mean is that the electric field equation, E, would be equal to KQ over R squared R hat, where Q is your source point charge. R is the distance away from that source charge that you are radially, and K is the Coulomb constant again. Now what this means is that electric field lines are going to point radially away from positive point charges. It's worth noting that not all electric fields for all charge configurations will have that radial symmetry. If, for example, you have two parallel plates, the electric field won't diverge radially, it'll point in straight lines in between the plates. So for extended charge distributions, you have to find other ways to draw the electric field lines and to figure out what the magnitude of the electric field is. The equation that I just gave you, kq over r squared r hat, that's for point charges, okay? Now, if you have a bunch of point charges, you could do superposition. You could apply superposition and find the electric field at any given point by summing up the electric fields from any of the other charges in the region at that point. So this would look like in an equation, k times the summation of qi over ri squared ri hat, okay? We'll do an example of this later when we talk about the dipole. In the meantime, it's nice to do this kind of thing conceptually by drawing electric field line pictures. The field lines give us a mean of representing the electric field pictorially, and they're really helpful, especially in the beginning stages when you're setting up what the electric field might look like for a charge configuration. So there's a few simple rules to remember. Remember that the electric field line vector E is going to point in the direction of the electric field line. So what you'll do is you'll represent your electric field lines as arrows, with the arrowhead pointing in the direction of the electric field. It's also important to remember that the density of the lines per unit area through a surface perpendicular to those lines is going to be proportional to the magnitude of the electric field in that region. So if you have a stronger electric field, your electric field lines should be denser and more closely packed than in a region where the electric field isn't as strong. So, with no further ado, let's talk about some examples here. Looking here at this picture, you have two surfaces, A and B, and you can see a few things and understand a few things about this intuitively. So first of all, you can see that this is a non-uniform electric field. The field doesn't point in the same direction at A as through B. You can see that it's starting to diverge and move away, and that the density of the field lines through B is less than the density of the field lines through A, and that indicates that the field is non-uniform. Now, speaking of specific charge configurations, what would the electric field from a positive point charge look like? Okay? Now, this is a 2D representation, and remember that field lines would point in 3 dimensions. Okay? But in this 2D representation, you have a positive point charge, a positive source charge that's a point. And away from that point charge, you can see the electric field lines pointing away radially. Now, another thing that you can get from this image is you can see that close to the charge, the field lines are closer together, right? And then as they move away from the charge, they are further apart. And this indicates that the field strength is getting less the further away from the charge that you get. And that makes sense given our kq over r squared equation that we saw earlier. Now, if you had the same magnitude of charge, but opposite sign, a negative charge, your picture would look very similar, except that the field lines would be pointing in towards the charge. So electric field lines begin on positive charges and end on negative charges. That's a little mnemonic I like to use to help remember that. Let's say that you had a dipole, which I'll talk more about in a second. A dipole is a positive charge and a negative charge of equal magnitude separated by a small distance. So a dipole, what that would look like is the electric field lines would start on the positive charge and end on the negative charge. Since they're in equal magnitude, you should have the same field lines, same number of field lines leaving the positive as ending on the negative, as shown here. So what would happen is in between the two charges, you would have a straight line here for the electric field. But you can see that off axis, your electric field is going to curve. What would happen if you had two like charges instead? Well, they would want to repel one another. The electric field in between two like charges, right smack dab in the middle, that would be 0, right? Because the electric field would sum to 0 at that point. So that's point C here. You can see that at point A, you would see the positive test charge over here more strongly. If you got really, really far away from both charges, it would just like you had one charge. It would look like one charge of magnitude plus 2q, right, instead of just plus q from either one. If you had charges that had not the same magnitude, then you would need to represent that by the number of field lines. So for example, here I have a positive charge and a negative charge, but their magnitudes aren't the same. The magnitude of the positive charge is plus 2q, and the magnitude of the negative charge is minus q. So you can see we have twice as many field lines leaving the plus 2q charge as landing on the minus q charge. If you got really far away from this configuration, your field lines should look like a 1 plus q charge, right? Just one charge of plus q, because that's what your net charge for that would be. And you can see, if you stare at it long enough, that that's kind of what's happening with that picture. Okay, so to summarize, lines begin on positive charges and terminate on negative charges. Remember to draw the arrowheads indicating the direction of the field. Remember that the number of lines, or the density of lines, indicates the strength of the field. No two field lines can cross. Remember, an electric field is really an indication of what direction the force is at that point. Charges don't get confused, right? So they know which way they feel the force. So if you had cross lines, that would indicate that the charge didn't know which way to go, and that's not the case. Remember that field lines are a representation, a pictorial representation that are used to qualitatively describe the electric field. They're not real things that you can touch. However, they do represent a very real concept, the electric field, which was thought of a long time ago by Faraday. Okay, so let's get into a more quantitative example now for the electric dipole. Let's calculate the strength of the electric field due to an electric dipole along the y-axis as the position shown in the figure. In this picture, I've done a red dot to indicate a positive charge, plus q, and a blue dot to indicate a negative charge, minus q. These charges are separated by a distance L in between them, which is small compared to the distance that we're going to look at the electric field at, which is indicated by the star here at a point P. Okay? So, to sum up here, we've got plus Q located at 0 plus L over 2, the blue charge minus Q located at 0 minus L over 2, and we're going to find the field at a point P at 0, comma y along the y-axis. Okay, along the direction connecting the line of the two charges. Okay, so what I like to do here is first draw my electric field vectors at the point in question. So at the point P, I've drawn a red arrow indicating the electric field from the positive charge at point P, and I've drawn a blue arrow indicating the electric field from the negative charge at point P. Remember that the field lines are going to point away from positive charges and towards negative charges. And that means that my red arrow is up and my blue arrow is down. Also remember that the positive charge is slightly closer to point P than the negative charge. And so the field strength from the red charge would be larger. I've indicated that here by the length of my arrow. Alright, so that's my pictorial representation of the electric field. Now what I like to do next is to write the magnitudes of those fields. In this case, since it's pretty easy to see that it's all along the y-axis here, I've indicated the direction of the field too with plus and minus signs. So here I've got plus q, the field due to that would be plus kq divided by the distance from point P to my red charge, which would be y minus L over 2, and then we square that. Remember that the distance in between the charges is L. Now, the magnitude of the electric field due to the negative charge Q is minus kq over y plus L over 2 squared. Okay? And this is just applying the formula that I had for the electric field for point charges that we talked about earlier. Okay, now that I've written down my magnitudes, I'm going to put it in vector component form and sum it up applying superposition for my electric field. When I do that, I get my total electric field E is equal to plus kq over y minus L over 2 squared in the y-hat direction. That's due to the positive charge. Now, from the negative charge, minus kq over y plus L over 2 quantity squared in the y-hat direction. Now I have to add these two vectors. So they have different denominators there, right? They're both in the y-hat direction, so the vector addition is pretty simple here. But the denominators are different, and so doing a little bit of algebra, I end up with E is equal to plus KQ times y plus L over 2 squared minus KQ times y minus L over 2 squared. And this is all over y minus L over 2 squared times y plus L over 2 squared. Now, expanding those squares up top and combining them, I get KQ times y squared plus YL plus L over 2 squared minus y squared plus YL minus L over 2 squared all over y minus L over 2 squared plus y plus L over 2 squared, all in the y-hat direction. Now, there's some things that cancel out. You can see I have y squared minus y squared and plus L over 2 squared minus L over 2 squared. So, when I combine those things, I end up with my electric field is equal to KQ times 2YL y hat over y minus L over 2 squared times y plus L over 2 squared. Now remember, we said to assume that the distance from the dipole y is much larger than the separation between the charges L. So if that's the case, then we can say that it doesn't make much difference if I add or subtract L over 2 from y, right? It's going to be approximately equal to then, therefore, KQ times 2YL over y to the fourth. And that's in the y-hat direction. Now I've got a y upstairs and a y to the fourth downstairs, so that cancels out one of the y's. I end up with the electric field is equal to KQ times 2L over y cubed in the y-hat direction. So that's our electric field. But you could stop there, but I'd like to take a second to introduce quickly the idea of the electric dipole moment, which is often symbolized by a P with a vector sign. The electric dipole moment is going to be the magnitude of each of the charges Q times their separation in between them, here indicated by an L, and it points in the direction from the negative charge to the positive charge, which here is y hat. So I can write the electric field due to that electric dipole as 2kp over y cubed, and that would be correct. Okay, so that's a simple example of an application of the electric field. I hope you enjoyed that. We'll do more in class, and I'll see you then.